Hi, I'm Juliana Haggerty. I'm head of our Centre of Excellence at CPI in intracellular drug delivery. Today, we're going to be talking about lipid nanoparticles in brief. So before we get into the detail, let's start with the basics of what is a LNP or a lipid nanoparticle. So the clue is in the name, really. They're made of lipids, which are a particular class of organic molecules, which includes fats and oils. And the nano just refers to the size. So these are really tiny particles, about 100 nanometers in size, which is about 1,000 times smaller than the width of a human hair. They're used as drug delivery vehicles. So think of it as a small packaging for your drug. So it protects it, it helps it get to the right place. And then when it's delivered, its payload or the drug to the right spot, then it biodegrades. For the rest of the video, we'll use the term LNP as an abbreviation for lipid nanoparticle. Some of the benefits of LNPs include their ability to package larger molecules, so mRNA and self-amplifying RNA. But also you can administer these same kind of formulations, these LNPs, multiple times, as we saw with the COVID booster vaccines. Whereas you're not able to do that with some of the alternative technologies like viral vectors, because your body actually develops an immune response against them. So now we're going to talk about how LNPs actually work. So LNPs are actually made of 4 different lipids. So the first one is a phospholipid, which is found naturally in the human body, surrounding all of our own cells. And then we also have something called a pegylated lipid. That just means it's got this natural polymer called polyethylene glycol on it, which helps enhance the circulation time in your body so it has a longer time to have an effect. Then we have cholesterol, which is used to add structure to the lipids. Again, that's a natural molecule found in your own body. But the really clever bit that allowed us to really make a breakthrough with the technology is something called an ionisable or cationic lipid. And this just means that the charge of the molecule, whether it's positive or negative, changes with the pH of the environment it's in. Usually, if they're 2 positive charges, they repel, or 2 negative charges, they repel. And if you have a positive and a negative, they bind together. So RNA has a negative charge as a molecule. So when you kind of have an ionizable lipid at a certain pH, you can make it positively charged, and then the 2 will bind and form a complex at the center of this LNP, and the other lipids will kind of fit and structure around that. It then has a role to play of when you inject that into the body, that's a neutral pH, and so this ionizable lipid becomes neutral as well, and that helps it prevent interaction in places you don't want in the body and reduces the toxicity. And finally, it's crucial during the uptake and release of the drug into the cell. And it's that change in pH when it gets in the cell that allows you to release and break up that complex between the lipids and the RNA, and then the RNA can go on and do its job. So one of the key areas that people are working on around RNA medicines and using LNP delivery vehicles is around cancer. So there's the potential to develop things called cancer vaccines. The other key areas are different types of infectious disease. So flu is a big area of research at the moment, but also genetic disorders such as cystic fibrosis, where you have an incorrect version of a particular protein, so you can use the LNP to deliver the instructions to make the right protein instead. CPI has been working in this area around LNPs since around 2016, and we now have a really kind of strong research group and capability with particular expertise in manufacturing these LNPs. We have an end-to-end capability from R&D, scale-up of manufacturing processes, through to being able to manufacture for clinical trials to go into patients. We were the first place within the UK that was able to do that for both the RNA drug or payload and the encapsulated LNP product. What's really exciting is we've just launched a new intracellular drug delivery centre with partners across the UK and universities and other catapult centres. And what that allows us to do is to go a little bit back into the research and solve some kind of key challenges around enhancing thermostability, being able to target different tissues and cells in the body, which will really open up a huge potential of different disease treatments and therapies. So what are we actually trying to achieve by bringing these partners together in the Intracellular Drug Delivery Centre? We're trying to make sure that we have the ability to develop and screen new LNP formulations, manufacture them, to open up the potential of this drug delivery technology. We also want to make sure that we are keeping the costs down as much as possible so that these new drugs are available to populations across the world. And that means that we need to start thinking about developing new lipids that are more cost effective and can be accessed by different drug companies. So that was lipid nanoparticles in brief. Thank you for watching, and do let us know what other concepts you'd like us to cover.